Our lesson for today will be looking at chemistry 1502. The topic for today will be looking at reactions of alcohols, dehydration, lesson 101.2. Let us start. And I have to mention it that the first lesson video for the dehydration of alcohol is lesson 101. So don't be frustrated to say you have skipped lesson 101.1. Lesson 101.2, it's actually a continuation of lesson 101. So in this lesson, we'll be looking at more examples. We'll be starting with example number 3, where we'll be looking at different examples. Let's say we want to convert a butanol I want you to understand that for the sake of being fast, you should know that here we have hydrogen atoms. So I'll just simply put these lines. So it's butanol. We want to convert it to alkenes. We know that this reaction, we are going to put heat, then we'll be using sulfuric acid. First step, this pair of electrons as usual, and then we are going to have, let me actually write it here. What is supposed to be here, let me write it here for the sake of having enough space. So we have our good living group, which has hydrogen and hydrogen here. Then we are going to have a positive. And then from here, our water molecule will actually leave. And then this is the part whereby it is very important. After the water is left, we are going to have let me actually do this. This will be our carbocation ion. And then, like I said, we have hydrogens. Let me put them now, because this explanation will actually be about this. And then plus water. We have our water here, which has left. I want you to understand that this is a carbocation ion, and it is a primary carbocation ion. The reason why we say it is a primary carbocation ion, you can see that this carbocation ion, it is only bonded to one other carbon. An example of a secondary carbocation ion would be something like this. This is actually a secondary carbocation ion. Then if it happens that we have a carbocation ion which is bonded to other 3 carbons, this would be our tertiary carbocation ion. You can see that it has bonded to other 3 carbons. Looking at this one, you can see it is bonded to other 2 carbons. It makes it a tertiary carbocation ion. Now when it comes to stability, this is the primary, secondary, and tertiary. When it comes to stability, you should know that the tertiary carbocation ion is more stable compared to the secondary carbocation ion, and the secondary carbocation is more stable than the primary carbocation. So what happens here in our example, this carbocation will try to be more stable, and the only way to be more stable is to become a secondary carbocation, because you can see that there is no way that we can have a tertiary carbocation. So in this case, this adjacent hydrogen, or the hydrogen of the adjacent carbon of the carbocation, will actually come here. We call this a hydride shift. If it comes here, it simply means that this carbon will have 3 bonds instead of 4, and then we are going to have something like this. So instead of 2 hydrogens, we have 3 of them, and then our new carbocation will be this one. So in this case, you can see it is a secondary carbocation because you can see that it is bonded to 2 other carbons. So this is an additional step that you should consider, and the shift of the carbocation, I mean the hydrogen, yes, the shift of the carbocation, it happens simultaneously with the water molecule leaving the substrate or the compound. And you can see that hydrogen has shifted from the second carbon to the first, and then the carbocation will also shift. This we call it a hydride shift, whereby the hydrogen, it shifts. Then our next step is when we have a proton loss. A proton loss can occur in 2 ways here. It's either these electrons will attack this one, or it will attack this one. Actually, not the one on the carbocation, or this one. Remember that after attacking, if we no longer have this, then this double bond will come here to form these 2 electrons will form a double bond here. Or if it attacks the first one, it simply means that this hydrogen is no longer there, and then these protons will form a double bond here. So we have 2 ways now. Let us go with the first one. If you attack this one, we are going to have a compound like this. We have a double bond here. Or if it attacks this one, we are going to have something like this. So you can see the difference here. The double bond is between the first carbon and the second, whilst here is between the third and the second. And then by the way, the mechanism is actually complete, and we can put our hydronium. So between the two, A and B, one of them is the major. Now, how do we determine which one is the major? Now we look at substitution. What is substitution? Let us start with A. You can see this is carbon number 1, this is carbon number 2, 3, 4. We look at these carbons, the ones which they are responsible for the double bond. We check how many other carbons are connected to this carbon. Looking at the first carbon, we can see we don't have any carbon which is bonded to this carbon, so we have 0 carbons. Looking at the second one, we can see that it is bonded to the third carbon, so it has 1 carbon. Actually, this one, it has 1, which is this one. And then let us compare with the next one. Is between, this is 1, 2, 3, 4. We look at carbon number 2, you can see that it is bonded to another carbon, so you can say it is bonded to one other carbon. We look at carbon number 3, you can see that it is bonded to another carbon. We do not include the one that forms the double bond with, so it is also bonded to another carbon. So in this case, we say this is disubstituted. Di simply means that we have 2 carbons. This one is mono substituted. The more carbons which are bonded to the double bond carbons is the one which is more stable. So this one is the major. Let us look at this example. You can go ahead and pause the video, try to work it out to see if you understand, and play the video. So in this one, we are going to have about 3 products. But you should know that the procedure is the same. Suppose this reaction, we use H3PO4, which is also an acid, and then the condition is we put heat. We know the first thing is protonation. Then we are going to have a new compound with a good leaving group. Have a positive charge. Then we have CH3 here. And then the leaving group will actually leave with a pair of electrons. Then in this case, we have to lose the proton, deprotonate. The reason why I said we are going to have about 3 products, let us look at this. Let me actually write this in detail so that we can see what is happening. By the way, this is a secondary carbocation. Our first product will come from deprotonating this carbon, meaning that you're going to have a double bond here. Or from here, you can see that this carbocation, the carbon which is adjacent to it, is a tertiary carbon. So this methyl group can actually come here. Since in this case we are shifting a methyl, we say this is a methyl shift. Then we're going to have a new compound which is like this. For you to see, let me actually write this in black. This is the methyl that has actually shifted. Then we have our hydrogen here. Then we have hydrogen, and then the carbocation is here. There's actually a problem here. Let me check. Okay, we have a methyl, so the only thing that is shifted is only this methyl group. So it simply means that our structure here, instead of hydrogen, we have another methyl here. And then bringing our deprotonating agent. There are two ways we can deprotonate this. Then we're going to have a double bond here, or we can deprotonate this to have a double bond here. Let me actually withdraw the second one. How about we deprotonate this hydrogen here to form a double bond here. I want us to write these products. It's the one that I've just rectified. The second one will be CH2 and then a double bond with our carbocation. Then we have CH3. We have C and CH3, CH3 plus the first one. We have CH3, okay, let me do this. We have CH3 here, CH3, a single bond, CH, okay, a double bond will be here because our carbocation. We have hydrogen here. Then we have our carbon here, which will be CH2. Let me just verify. This is it. You can see the double bond is here, and then this proton was actually removed. So these are the structures that we can have if we dehydrate that particular compound. And just to rectify, this should be 2 here. Now, which one is the major one? We have 1, 2, and 3. In this case, we have to check the substituting. Looking at the first one, these are the carbons we focus on. So we have 1, 2, 3, 4. We have tetra here. In this case, we have this one and this one. We only have 1, 2. We have 2 carbons here. This is tetra substituted. This is di-substituted. Then looking at the last structure, we have 1. so it's mono-substituted. So you can see that this will be the major, then I don't know if we call it the middle, and this will definitely be the minor. Between the major and the minor we have this one. That's it for this lesson video. This is Paula SJ. Thank you very much.